Now, do you know what acoustic detection is? The managing director of the company Marlinks explains us why the best mates are actually better on shore. He tells us more about the added value of distributed acoustic sensing. Here is for you Roel Vanthillo.
Good afternoon. And directly relating to the previous presentation, I really want to present something with regards to acoustic monitoring. That's the distributed acoustic sensor, DAS. And with this new sensor, we can turn an ordinary fiber optic cable in an array of 1,000 microphones, because it records every acoustic vibration or strain event in a fiber optic cable with a spatial resolution of 5 to 10 meters. This means that, for example, if you have a 50 kilometers long cable, you will get 5,000 virtual microphones in this cable that then record acoustic vibrations between 0.1 Hertz to 1,000 Hertz events, make it ideal for monitoring pile driving, marine mammals, and stuff like that. And that is exactly what I want to present to you today, some use cases of what distributed sensing can be used for and how it can be used in the offshore wind environment. So first of all, for example, as also been mentioned during the previous presentation, pile driving is a hot topic, and especially the sound emitted during this pile driving. Well, we did some small-scale testing with it in our lab, where we applied just a small cable with some fiber optic inside it in this aquarium, and then in the meantime, we will make a hammering sound to see if it's indeed detectable, and you will see that in the right bottom corner. So I will start the video right now.
3, 2, 1. 3, 2, 1. Poof.
So as you notice, the pile driving activity is immediately visible on the screen and immediately visible, detected by the sensor when it's happening. And this is not only the case for example, pile driving at that location, but we can really differentiate between pile driving locations at different locations, or we can see where the sound level is the highest or the lowest, or how it reduces over the distance. So that's a very interesting measuring opportunity that is possible with such a system, because you don't have only one hydrophone or an acoustic sensor, but you have thousands of it that you can combine to assess the sound which is emitted by the pile driving. A second example that I want to show to you is the mechanical impact monitoring, not related to sound, but more what movements are detected by the cable, because also this creates a vibration which you are able to detect. So in the next movie, you will see that the orange box will start moving very, very slowly, and actually it shows, or it simulates some kind of a wave motion, the movement of a topside because of wave actions or tidal streams. And it's a very subtle movement, but still this will be visible also on the DAS, as the fiber optic cable which is wound around the tube is changing and is deforming. So it's a very subtle movement, so we'll start the movie right now. So you see it in the bottom corner, you see it running. And now we zoom in, you see indeed a very small movement, but still these vibrations are detected, meaning that the device is really sensitive to even the slightest movements in the cable, making sure that we can detect, for example, also bending radii from cables or strain applied to the cable. So that's the second thing which is possible with distributed acoustic sensing, not really then related to acoustics, but really to mechanical movement of the cable. The third one, maybe the most interesting one, or the most, if you look to the environmental aspect, we can also detect marine mammals and really count them. And for that, we use, for example, the example here where a Bluetooth speaker is again entered into an aquarium with a fiber optic cable in it. And the Bluetooth speaker will play the sound of the North Atlantic right whale, so a very endangered species. And you will see in the bottom corner again what sound is depicted by the sensor. So this was the example where we detected the North Atlantic right whale, and here you see in the graph, in the top graph, you see the image that was sensed by our sensor, so by the DAS, and in the bottom graph you see the real spectrogram of this North Atlantic right whale as was played in the audio clip. And you see there's a very clear resemblance between the two, meaning that with machine learning techniques we can really identify and that this sound belongs to this type of species, and can make an assessment and can count the amount of whales passing by, detect where they're swimming, and also make all types of analysis with regards to migrating speed or migrating patterns in case of, for example, external acoustics or just natural behavior. So these are some examples what we can do with acoustic monitoring. Of course, we also have some reference cases and some achievements so far. So first of all, something we're very proud of is that we were able, with a fiber optic cable connected to a distributed acoustic sensor before the front of the coast of Belgium, we were able to detect an earthquake in the Fiji Islands. So 16,000 kilometers away, but still this vibration is passed through the soil to the oceans, and we're still able to capture it, as the next slide proves. So the bottom graph is the graph from the land station in Ostend, and really this place here, and the top graph shows what is recorded by the DAS. And you see that although the image is more noisy, you see clearly that the earthquake was detected. And it was not always, not only said by us, but we did this in collaboration with 2 universities, and it was recently also published in Nature Communications as proof that it is really valid and accepted by the scientific community. Another example is that, for example, we were able to detect the acoustic vibrations of ships passing by. So here you see the output from the sensor from shipping lane at Scheur in front of the coast of Zeebrugge, where you can see in the bottom graph those marks are actually ships passing by, and we measured those with a cable which is buried 6 meters into the soil. So even first 20 meters of water depth and then 6 meters of soil, we're still able to detect the vibrations of ships passing by and pinpoint which ships is which when it's passing by of the cable. So these are some examples of what fiber optic monitoring is based on distributed acoustic sensing and how it can assist in operations of offshore wind farm.
Thank you, Roel, for this really interesting explanation. Now, someone wonders, can acoustic sensing only be used on new cables or also on existing cables?
It can be used both on new and existing cables, because the only thing we need is a fiber optic cable inside the power cable, and basically in all modern power cables, fiber optic is embedded, and there are plenty of fibers free for monitoring systems as distributed acoustic sensing.
Okay, thank you.